אלא יותר ברמה של approximation, יש את המאמר הזה של ארג'אנצוף ופרנסקו, ליניאר סופי, על קצין הזה אולי, כי שם הם ממש מדברים על חבורות שמקורבות על ידי כזה שרק מטריקה. זה אותו דואו, אבל כאילו זה מאמר אחר שלי.
למה לא רואים אותם?
כאילו ביקשתי ממנו אחת המוטיבציות לזה, וזה דווקא די מגניב, שכאילו שזה עוד דרך אפשרית למצוא חבורה שהיא לא סופית נגיד.
כן.
כי נכון, יש את זה הקלאסי שאתה רואה, שאם יש לך חבורה שהיא לא רזידיולי פיירטים.
לא, אבל זה מה כאילו לא פתוחה משום.
אז מספיק לעשות את זה נגיד בשדה סופי. מספיק שאתה לא סטבילי באיזשהו
אפילו שדה לא סופי.
לא, אבל אתה רוצה, כי אתה רוצה שזה...
זה עדיין חבורה ליניארית, זה לפעמים.
כן, אבל אתה רוצה כאילו אתה רוצה שבתיקון אתה מקבל שאתה...
המצלמה הזאת עובדת, שזה השנייה.
כי אתה רוצה...
זה לא עובדת.
נראה לי שבגלל שהפאן סמינר הפך להיות זום, אז כולם הפכו לזום.
אין בעיה, אבל למה זה...
לא, ההפך, דווקא... הפאן זה לא חסם תחתון, חסם עליון, כי הוא כאילו...
אני לא יודע מה לעשות.
לא, אבל יש אנשים שמגיעים
מישהו ניתק את זה?
בשביל הפאן.
כן.
יש את זה, לא ראיתי כיבוד בחוץ.
לא, וירטואלי יש את זה. זה אותו דבר עם הכיבוד.
אין לי מחשב פה.
לא, זה פשוט לא מחשב.
ככה זה היה לנו שנה שעברה.
אמר לי אם אני יכול לעזור איכשהו, אני מרגיש קצת יוזלס. הנה, מעולה. זה היה חיבור.
אבל זה...
זה בסדר גמור. יופי, יונתן. אוקיי.
לא הרשימות שלך מימים.
וגם את הרשימות שלי.
מה ששיר לי גפל פעם שלך.
לא. לא, למה למדתי את הדבר הזה? זה לא גימדתי את זה.
זה קורס, כאילו...
תראה, גברתי כוכב כללי, כן, למדתי. טוב. אז מה לפעמים פעם שעברה? פעם שעברה, אוקיי. So last time we started the discussion about injectivity in general categories, right? And so, okay. The main thing last time was proving Armstrong's extension theorem, which shows that B of H is injective in the category of operator systems and UCPs. And then we discussed about general injectivity, so I will remind you that reminder. This is also not good enough. This one should work. No. פשוט במצלמה, צריך להיות ממש טובים.
יש לי טושים ממש טובים בה.
אתה מביא?
אני מספיק או שאתה צריך ירוק?
שחור. So reminder, if C is category, if C is category, an object I is injective if whenever we have an embedding, so we discussed what are exactly embeddings in a category. It means that I can sort of it as like I have an isomorphism from X onto its image. So whenever I have an embedding and a map from the small one to I, then I can extend it to the big one. And we gave some examples. I just remind you briefly. So P of H is injective in the category of even operator systems and UCP. Field is always injective in the category of Banach spaces with linear transformations. This is just Dan Banach. We show that for C-star algebras with star morphisms, there are no injectives, but in the commutative case, there are, and I gave you an exercise to describe where they exactly. That for groups in general, there are no injectives except of the trivial group, and for a billion groups, these are exactly the divisible groups that are injectives. And so today I would, okay, and before going back to our category, I just want to say something general that you can always do. So claim if you have something, I don't know, some J that fits inside I, and I is injective, then J is injective if and only if I can extend the identity map on J to a map from I to J. Right, and I mean this is almost immediate from so proof. Right, if well, which direction? Let's start with this. This direction. J is injective. So I have this map, right? So there's nothing to show. Right, if J is injective, then of course I can lift any map. Injectivity. Conversely, I need to show that J is injective. So I need to show that whenever I have X inside Y, then I can, and I have a map from X to J, then I can lift it. I don't know it for J. However, I do know it for I, right? I do know it for I because I is injective. So I can take this map and lift it to a map from Y to I because I is injective. But now I'm assuming the right-hand side. So I can go down like this in a way that preserves J, in a way that right, in a way that extends the identity, right? Maybe, okay, I think it's clear like this, right? So I do have a map from Y to J that extends this map X. Okay. So this is just a categorical fact. In our case, so back to OPSIS operator systems with UCPs, as so a corollary from this claim, as let's say, okay, we can always put an operator system inside P of H strictly, right? I mean, infringement. As inside P of H is injective, if and only if there is a UCP projection from B of H onto S. Right, so I think again, I think of S as sitting inside B of H, and what I said here abstractly, I can do it concretely, and say, okay, I really have a UCP, right? It should extend the identity, so it is to be a projection. Fine. Please interrupt me from time. Good. So let's give an example. Now that we know, okay, we already have one example in our category, B of H. Yes, Alan?
So a small question. So like when people say a von Neumann algebra is injective, they mean in this sense.
Yes.
Right?
when people discuss about semi-discrete phenomenal algebras or things like this, yes, they mean in this sense, in this category.
Right.
So this is something you start feeling at this point, that why this category is spatial. This is one of the reasons. I mean, the reason that we're going to see today somehow, and it relates to nuclearity, and it relates to many notions that doesn't work well in the category of sister algebras with star homomorphisms, in the category of phenomenal algebras with normal star homomorphisms, etc. So, and it's interesting also in the commutative case, because also there it doesn't work. And then if you go and read some classical theorems, you come up with these weird theorems saying, if I have a map from my space to the probabilities over the other space, but this is exactly to say that I have a UCP between the corresponding continuous functions over the space, etc. So this is one of the reasons. So I'm saying that this corollary allows us to construct many nice injectives. For example, think about let's say right, I can think about B of L2, little L2 of N, right, as big matrices, like infinite times infinite matrices, right? And I can take I have a UCP map that kills everything but the diagonal, right? So I mean, it's not hard to construct this map, right? I can describe it. So just kill everything, but keep the diagonal. This would be a UCP. I mean, it's a really easy exercise to solve. So I have here a UCP map, and a UCP projection. From, so what is this diagonal, right? I can think of it as L infinity of N, right? Why is this UCP?
No, why is it?
So you're asking why a diagonal of an element here needs to be bounded, or why? Okay, I mean, so one direction is clear.
Look at it also as L2.
What?
You can also look at it as L2.
No, it's more than that. L infinity is more than L2, right? So think of the identity operator. It's 1, 1, 1, 1, 1. It's not in L2.
L2 would be Hilbert-Schmidt.
L2 exactly the Hilbert-Schmidt. So if I take this map and restrict it to the Hilbert-Schmidt operators, I will get L2. Or to the trace class, I will get L1, etc. But in general, it's L infinity. And to the compact, I will get little C0. Yes?
You think about it as appelization of B of L2 N, right? And this is the commutative algebra.
Right. Right. I don't want to discuss about phenomenal algebras, right? So I'm just saying that I can always do this, and this shows that L infinity of N is injective. So L infinity of N is injective. Now, just something, maybe I'll give you it as an exercise in injective. Maybe I will do it later, I'll see. But fact, C of X is injective in this category implies it is injective in unital sister algebras with star homomorphisms. Okay. Implies, this is something you show in the exercise, that X is extremely disconnected. Namely, a closure of every and tens of. I gave you an exact, הדרכה, how to do it, how to show it. I told you exactly how to construct, how to embed C of X inside C of Y, and with this Y is going to be somebody very specific depending on the choice of the open set you choose. And then from this, you show that, from the injectivity, you show that the closure of this open set needs to be open again.
What about the converse though?
I didn't give you proof the converse, but you can open, I can refer you to the where to see it if you want to. Or you can prove it yourself. It's not that difficult, but I give you one direction, which I thought would be enough. Anyway, just in particular, I just wanted to mention Beethoven is injective. Is a formalistic, right? Right, L infinity of n is a commutative sister algebra. So it's continuous functions over something. This something is exactly the stone check compactification. You can take it as a definition, or if you have another definition, you can prove that is the same. More generally, maybe I want also to add a more general example. 3, more generally, if H is an Hilbert space and D is discrete, think about N, but just a discrete set, and H is Hilbert, I can do the same thing from B of L2 of D to H. So these are just H-valued sequences over D. Okay. So you can, if you know tensor product of Hilbert spaces, this is nothing but L2 of D tensor H, or direct sum of H copies of itself D times, direct sums of H with itself D times, in the Hilbert sense, to complete it. Anyway, so you have this projection that goes from here to L infinity of D. So it will be B of H value. So this is just a small generalization of that. So this will be a GUCP projection. GUCP projection. For L infinity of D, B of H, value is injected. And maybe put a little star near this fact, because I will call it next week. Okay.
You will what?
I will use it. I will remind and refer to it. But is it clear? And in this way, I can construct many injectives. And also, what I'm going to say now is going to come from this fact, which was very general, I remind you. This fact is true in any category. That's the way that's going to help me to construct the injective envelope that I'm now going to describe and construct. So before that, yes.
Just a smaller tehiyah. So these UCP projections in 1 and 3. So like Stansfield tells us that there should be compression by a core, like there should be a core compression of a star homomorphism, right?
Right.
All I'm asking is whether, like, in the identity representation of BH, for example, is it like what is the projection that we compress this by to? Like, is there a subspace?
It's just like, there's nothing. S is B of H, right?
S is what?
B of H. Here. In what?
No, sorry, in 2. In 2. Well, I'm talking about 2 and 3.
Compression?
Yeah.
Okay, so I don't know, but I can tell you how to find it.
Okay.
You can take many compressions that you know how to construct. Like think about the finite rank projections that will do it. I mean, finite rank. Okay, so you can describe them first as some of these, and then go to upper levels, and then you know that the UCP maps in the BW topology is closed, and somehow you're looking for the limit. So there is somebody who will do the job, right? But you can also, I think you can also, I mean, if you want to concretely find the projections themselves, I think you just need to go to finitely many copies of this guy, into infinitely many copies of this guy, and
right.
You'll be able to do it. We can try to do it. Okay. Anyway, so before doing this, something like a really remarkable fact that we have for these guys, for such maps that are UCP projections of B of H, is that these guys are always sister algebras. So let's see. So theorem that is due to Chorin-Nephos let S in B of H be an injective operator system, and let P from B of H to S be the corresponding UCP projection, then setting, so for every A and B in S, S is not a sister algebra, but it sits inside the sister algebra. So I can multiply A and B in B of H. Now I can take this product and project it back to S. So I do this very weird thing, hoping it's going to work, and defining like a new multiplication on S, just being very naive, saying, okay, multiply them wherever you can, and then use your projection. And this is, so then setting blah, 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 makes S with the usual star, the usual norm, and this new multiplication a sister algebra. And the identity so okay, I'll explain it. It looks weird for a second. The identity from S to our new sister algebra is UCC. Unital completism. So let me ask you first: do you all really do you understand the last statement? I mean, what do I want to say by the identity uses? So look.
Okay.
Yeah. So do you want to explain it?
No, wait. I'm confused. You say S and this multiplication is a sister algebra, and this is the same norm?
Yes.
So what
so these guys, they are a part of our original S. They are coming from B of H. These are not new. Nothing is new, right? Original.
What do we know about S?
Original.
It is
I understand what you mean.
Operator system.
okay.
Injectable.
Because on the amplification.
Well, I'm not going to use injectivity. The only place I'm going to use it is that they have this map. What?
Because on the amplifications, you have a norm coming from
Exactly.
BH,
so
and you have a norm coming from this system.
Exactly. So what Alon says is that obviously this map is isometric. The norm here is the norm here, and the identity is the identity. No problems. But we have the extra baggage. We have M and S living here, and here the norm they get is from B of H. Right here, the norm they get is from the fact that I put them in B of H DN. This, on the other hand, is an honest to God sister algebra. Maybe, I don't know, maybe it sits inside another B of K as a sister subalgebra. Anyway, it has its own product, and therefore it has in its own Mn of S that are sister algebras. So these guys, they have their own Mn of S that they're sister algebras, and it's not clear at all that the method goes from these Mn of S to these Mn of S. These are now different norms. The norms of these guys coming from the fact that this is an operator system, and the norm of these guys are coming from the fact that this is sister algebra. It's not clear at all that the norm, the identity will preserve the nth norm, or in other words, the identity will be useless. This is not clear, and this is also something I want to show. Okay.
So you're saying that every injective operator system is of this form, right?
Yes.
So you're saying injective operator systems are sister.
Exactly.
What happens if they are? Okay, this is maybe a follow-up question, but
yes.
when do they become von Neumann algebras?
That's
because like in Furstenberg boundary, the Furstenberg boundary is the measurable one. It's what we want.
It's a very good question. So in the commutative, okay, let me just briefly say, in the commutative case, what you get are exactly so-called AW star algebras. And if you read a little bit this book that you told me, then you know that, well, that in general there is a difference between being AW star algebra to being AW star algebra. But again, you can discuss.
Okay, cool.
Yes.
The opposite is not true, right? You have C-star algebras that are not injective?
Many. Again, in the commutative case, we know exactly that the injectives are going to be very specific ones, those that your Gelfand spectrum is extremely distinct. Okay.
This is what they call Choy-Foss multiplication.
This is what is called the Choy-Foss multiplication or the Choy-Foss product, and it is something very general in a sense, right? Whenever I have such a UCP projection or a conditional expectation, in some sense, I can do this. Okay, so proof. So let's see what we need to show. Well, first, we need to show it is an algebra. Well, it's an algebra. What do I mean by showing this is an algebra? I need to show that it's closed under. Okay, this is clear, right? From definition, it's closed under. I need to show that this is a distributive that one is trivial, that it is associative. Tell me if you think one of these guys is not immediate. So closed under this is of course immediate. Distributive. So if I write here B plus C, and then here I write B plus C, and I can open everything, right? Because phi is linear, so it's immediate. 1 multiply here 1, it's multiply 1 in here, it does nothing, so it's immediate. Associativity, associativity is not clear, right?
This needs Tomiyama, no?
What?
You need Tomiyama.
Right.
Like why is 1 immediate? If you multiply A by 1, you get phi of A.
Yes, but phi is a projection. Right? It's the identity on S, I suppose. So associative. So I need to show that right that A times B times C, it's A times B times C, namely that phi of A phi of BC is equal to phi of AB C. Yes. This is what I want to show. And enough to show the following claim, enough to show a claim for every X in B of H and A in S, phi of X A is equal to phi of XA, and phi of A of phi of X is equal to phi of A of X. Why is it enough? Do you see it? Right, because then well, if we show the claim, then put instead of X, I don't know, BC, okay, it's not the right order, but fix it. Then have phi of phi BC times A is equal to phi of BCA, which will be equal to phi of BCA, which will be equal to A of phi BC. Just change the name accordingly, but this will show. Do you want me to show it? Okay, just one line. Let me write it. It doesn't worth thinking of it too much. This is enough, since assuming the claim, phi of A phi BC by this part is equal to phi of ABC, which is phi of ABC, which by this part is phi of AB. So this is the claim. Okay. So proof of the claim. So proof of claim. So I'm going to apply the Schwarz inequality on for phi2 on the matrix A star X 0, 0.
Sorry, Guy,
Yes, Alan?
I'm confused. Like, we said that Tomiyama says that phi is a bimodal map, no? I mean, phi is a UCP projection.
Sorry, but this is not a C star.
Not a C star. So my mistake.
Yes, right. You said before Tomiyama and
No, it was my mistake.
Right. No,
It's my mistake.
it's the same reasoning and more or less the same proof.
Sorry.
You're not that wrong. it's just
Proof of
it's not a sister. But yes. So the idea is like we're applying Schwarz inequality on this thing. So what's the point? So we know Schwarz inequality tells us what, that phi2 of V star, this is greater than phi2 of A star X 0, 0, sorry, of A X star 0, 0 times phi2 of A star X 0, 0. Now we just need to open everything. So on the left-hand side, we have A star, phi of A star, and phi of A x, but phi of A is just A, so it's A phi of X, because A is in S, everybody. Phi of X star and A star, I think. No, I'm doing something wrong, right? Or is it okay? And here phi of X star X. So this is the left-hand side. And the right-hand side is what? Is, well, the same thing, but all phis on everybody, right? So here just get A star, and here A phi of X, and here phi of X star A star, and here phi of X star phi of X. Does this make sense?
What is left-hand side? What is right-hand side?
That's the right-hand side. And that's the left-hand side.
I mean, when you open up this.
So I multiply these two matrices and then I apply phi on each entry. That's the left-hand side.
So why is it A phi of X and not phi of AX?
Phi of A is A. Phi is the identity on S, and A is in S.
But why? So you're claiming that phi of A. So you're claiming that phi of AX equals A
here
of PX.
you're saying why here I didn't throw phi of
No.
A. What?
I'm actually.
Where is the part that is not clear?
Which of the left matrix is the left-hand side?
Like this.
Yes. So I'm asking why is on the left matrix, the upper right entry? Yes. Why is it A phi of X and not phi of AX? Maybe I'm confused.
No, maybe I'm confused. You're right. This is my mistake. Thanks. And this is exactly what I needed.
Okay.
Sorry.
Because we don't know that it's a
Right,
bimodule number.
Right. Yes, exactly. That's the left-hand side. This is the right-hand side. Right? Oh no.
Yes.
Do we have a problem? You're not satisfied with some reason?
Yeah.
Is it okay?
Yeah.
So now let's do something very, very cool and apply another time phi2 on this. Phi2 is positive, right? So let's apply phi2 on this. All of this, I want to apply phi2. So nothing is going to happen to the left-hand side because it is phi's projection. So phi composing with phi is phi. So the left-hand side matrix is going to stay the same. The right-hand side matrix is going to be phi of A star, and that this was the point modulus. Phi of A, phi of X, phi of X star, A star, phi of X star. I don't care in fact. So here's the point. The point is that I got here and here the same elements. So if I subtract this from that, then I get 0. And it should be a positive matrix. And for a positive matrix, we already saw this a couple of times. It means that these guys, the differences here are also zeros. So the difference is positive. Difference is of the form 0 something star something, and is positive. This implies that something and something star are zeros. So this gives us exactly what we wanted. So phi of AX is phi of A phi of X. And similarly, we have the other direction. The other right. Oh, yes. Oh, just by a blank star. Good. Okay. Okay, so questions about this? Or is it cool? I mean, it's very cool. I just want you to know this. We used only the 2 positivity of phi. We used it twice, but we used only the 2 positivity of phi. So in fact, we proved something more general. In fact, we proved that whenever we have a two positive map from B of H on to S, then S is an algebra. Star algebra. And well, now, so I said I'm leaving this on the blackboard because we proved it's an algebra. But I mean, it wasn't that easy, but now we have associativity as well. Now we want to, so this was, let's say, 1. 2, so okay, well, what?
What about the C-star identity, for example?
So yes, okay, I'm just saying, okay, so now this is a star algebra. I mean, okay, there's nothing really to check, right? A, B, star. This is because phi is a star, right? Because it's UCP. It's phi A, B, star, which is phi of B star, A star, which is B star, B star. Right, this is identity the star, of course, it's an evolution. C-star identity. The fact it is a C-star algebra. So we want to show that A star times A, which we know by definition is phi of A star A. Clearly, it is less than or equal to A star A, which by the usual C-star identity is the norm of A squared. So one direction we have, right? Here I only use the usual C-star identity, but I only prove less than or equal to. Why is it also greater than or equal to? So why?
You actually need the first equation for like A and B, right? Because you want to show it's a Banach algebra.
I need which equation for A and B?
Like the first line.
You want me to show first it is a Banach algebra?
And that's like private case.
Right.
Just
Sure.
formally.
Formally. Thank you. So let's put here in before, maybe this is only 4 and 3, it's a Banach algebra. And this is the same proof, right? A times B is phi of AB, which is less than or equal to A times AB. Okay. So it's a Banach star algebra until this point, and now this is star identity. So one direction is immediate from the fact that it is a Banach algebra, and the other direction, well, it's from the Schwarz inequality, which is very useful. But phi, I remind you, phi is a projection, so this is just A star, usual A star. Good, so now we know we have a sister algebra, not just
I'm so sorry for being pedantic.
no, please be pedantic.
We should just say
I
that
also need to say that from this point, more or less, I'm not doing it from exactly a ranged book, so it's good to be pedantic. Yes.
So we should also mention that it's a Banach space because it's the image of a closed, like a map with a closed image, right? Like it's the image of the.
I think you're just a closed space and a Banach space.
What we didn't require operator systems
to be closed in this course. By the way, sometimes people do require it to be closed, but right, it's an onto a surjective image of a Banach space.
No.
You're saying it's not clear that
It's because it's a projection.
it's a projection, right? You're saying just by surjectivity, if a norm is projected image of a Banach space.
No, there are operators on Banach space subject.
I don't know, but you're right. A projected image of a Banach space is certainly a Banach space. This is,
Should be,
this is,
yeah.
So right. So thanks. So maybe we should also somewhere here just mention it's also a Banach algebra. So let me write here. 1 point f. It's a Banach algebra. It's a Banach space. Banach space. Okay. I mean, there's another way to see it, but
Okay.
fine. I mean, right, a projective image of the Banach space, projective image of the image. So now I want to prove the last requirement that the UC that S is uniton completely isometric isomorphic to S. One comes with extra baggage from B over H, and one comes from the extra baggage from this new multiplication. And the idea is the following one. So suppose, so okay, what I want to say is like we have, we want to show, we need to show that when I take the identity map from M of S coming with its usual norms from B of H, and I take the map to our Mn of S with a norm that coming from the fact that we have a product. So whenever we have a product, we have a unique norm, right? This is a sister algebra. So if I see sister algebra, then also this guy is a sister algebra. That's like the product on the matrices. And whenever you have a product on it, whenever you have a sister algebra, then its product knows the norm. How come? Just remind me. Because we have spectral radius. Yes, we can recover the norm from the product. So what I'm going to show, okay, so what is this product? This product, I know, yeah, let's check it. I don't want to. So if A is Aij and B is Bij, then A times B, A this product times B, the Ij's coordinate is what? Well, we have to multiply it as we multiply matrices. So this is K goes from 1 to N, A, I, K, B, K, J. But now this product is just phi of AIK, BKJ, which is phi of the whole sum, because phi is linear. What is my point? My point is that this guy that sits inside phi, this guy is just the ijth entry of the usual product of AB as sitting in B of H to the n. So this is just phi n of the matrix A times B, usual A times B, the ij coordinate of that. Do you understand what I'm trying to say? Okay. So now what we learn? We learn that this Mn of S is also of this form. I mean, there are several ways to say, but I mean, okay. Let me say it. I mean, most in a straight way. So, what's the product on these guys?
Product on HM.
Normal matrix.
Yeah. So what? Okay. So. Okay. Let me do it.
Keep going.
What I want to say is that this phi n, well, we know. I mean, we know that on the level where we have the projection, the map is isometric. And I'm just telling you, we have the same thing now that we know that this new multiplication comes from. Okay, I need to write it in a correct, I mean, in a arranged way. So let me now that we made a computation.
So basically, the first item just prove it for the normal multiplication that we have this isomorphism, right? Then what you did right here just to prove it to higher dimension.
Yes. So let me rephrase it like this. Now, phi n goes from B of H. I can think of it as goes from B over H to the n onto Mn of S. Thinking of Mn of S as an operator system. This is also a UCP projection, because the original one was a UCP projection. Therefore, this Mn of S has its own Choy-Force product that's denoted by n. Right? This is its own Choy-Force product. And is isomorphic, just isometrically, I'm not telling more than that, isometric to the usual Mn of S. But now we saw, but what is this? What is this product? This product is exactly this one, and we show that it agrees with this one. Therefore, because of the uniqueness of the norm for sister algebras, the norm has to agree, because of the uniqueness of norms for a sister algebra, the norms agree. The norm of this guy, which we know is equal to the norm of this guy, which now we know we have the same product as this guy, therefore the norms agree. This is a sister algebra because of what we proved. Okay, so there is a trick here, but I hope I convinced you. Good. So now we know that, okay. So now, definition. Let S be an operator system. I'm not writing it. So S an operator system. An extension. So an extension is just another word. Extension is just another word of saying embedding. Embedding is when I think about the small guy, and extension is when I think about the big one guy. An extension I of S, so meaning I there is a uses or embedding in general kappa from S to I. It's called an injective envelope. It's called an injective envelope of S. If I is injective, and if it is minimal in the following sense. Well, in the sense of containment. And if it is minimal, and if it is minimal in the sense that whenever I have an I prime sitting between kappa of S and I prime injective, then I is equal to I prime. Okay. So our goal is to prove that every operator system admits an injective envelope that we now know is going to be also a sister algebra. Okay, but our goal is to show that any operator system. By the way, it's not easy to show even that any sister algebra admits an injective envelope. As we said before, it's completely unclear. I mean, it's not true that any sister algebra is injective. So it's even interesting to think about injective envelopes for commutative sister algebra, right? But think about it later if you want. It's something called the Gleason cover, when topologically speaking, but I don't know if you've ever heard this notion. Anyway, think about, suppose I give you to prove it as an exercise. What will you try to do? To prove that there exists a minimal injective envelope? You will try to do a kind of Zorn's lemma, right? You will say, suppose, well, I just need to show more or less that whenever I have a chain of injective things, then their intersection is going to be injective again. But you will fail. It doesn't work. And I think this is one reason, I mean, it is tricky, this thing. So here's a nice trick that Hamana came up with. I mean, I think it's a very good trick, but nothing. So maybe just remark, a naive Zorn's lemma will fail. Zorn's lemma fails. So for that, I will need the following notion. Definition. Assume S is an operator system sitting in B of H. We call phi from B of H to itself an S map provided that phi is UCP and phi of A is equal to A for any A in S. I'm not claiming it is a UCP projection, be careful. I'm just saying you are the identity on S and you're UCP. An S map such that phi composition with phi is equal to phi is called an S projection. Again, I'm not claiming this is a projection onto S, a UCP projection onto S. Maybe it's it can be a UCP projection to something bigger than S, right? And still it will be the identity on S. We can also think of an S projection. We will also think of an S projection as a UCP projection.
Is the indicator?
No, as a UCP projection just from B of H onto its image. Nothing else. So okay, S sits inside, but because it's an S projection, but nothing else. I mean, this does not have to be S. We define a partial order. We define a partial order on these guys, on S projections. Why? We say that psi is smaller than phi if psi composing with phi is psi, which is phi composing with psi. If it's small in the only way that you can think math can be small. And given an S map, phi, we define an S seminorm P phi on B of H just by calling P phi of X to be the norm of phi of X for every X in B of H. And for seminorms, we have a usual, right? We say that, well, there is a usual, I mean, even if it's not P phi, for seminorms in Q, we say that, can always say that P is less than or equal to Q if P of X is less than Q of X. I mean, I just recall here that in these guys, we always have an order, a partial order no matter what. What we're going to show after the break is that we can find the minimal S seminorm. And then we will take the associated phi, right? The minimal S seminorm meaning it comes from phi. We take the associated phi. The associated phi will give us such a map, and this guy here will be injective because it's an image of injective, so it's injective, and it will be this will be the minimal injective number. So this does the job. So the fact that Amanda thought that you can do the zone's lemma on something else, I mean, was a good idea.
You will prove that this specific phi will be minimal in the sense of what you write above?
Yes, this P phi would be minimal in the sense. I will also prove that this phi would be minimal in this. I will find it from here, but I will show it is also minimal in this sense. Okay, let's take a 15-minute break, or maybe let's meet in 1 and 2 minutes, and 3 and 2 minutes, because I want to finish everything today that has to do with I want to start the dynamics next week. So I'm going to make some tea.
אז מה אמרת לתגובה ל... לא, make your tea.
הייתה שאלה?
לא, לך. go drink.
בסדר, בוא תלמד אותי.
סתם, כאילו, אז מתי זה יוצא לנו? אני לא יודעת, כאילו, קצת לעשות שואל פה ספורט.
לא, זה לא בדיוק, לא בדיוק יוצא לי. לא עכשיו, שאלה היא מתי, היא ג'קסטי סטינג, היא גם לא לעשות. כן, זה לא דבר. לא חושב שידוע שלו, אבל...
זה 10 דקות עכשיו או לא שעה?
עוד 12 דקות.
כאילו, לי היה, מה, אני הייתי צריך. כן, זהו. It's the wrong question. No. It's not the right question. No. אני עוקב. לא יודע, תורת מימד, פונקציות יוצרות וזה. שנייה. מה אתה רוצה?
אני לא מוכן ככה.
מה אתה רוצה יוצרות? כדי להראות נטר מקומי יש מימד. כן. לא, כל בסדר, אבל כדי להראות שמימד הוא סופי, צריך כזה.
רגע, ואתם עושים עם...
מה?
אתם עושים עם גיאומטריה אלגברית?
בקושי, כמעט לא. טוב, רק מספרים אלגבריים מאשר.
מה קורה יארי? מה המצב? בסדר.
אז אם אנחנו מגיעים למערכות דינמיות, זה ממש מתחיל בסוף.
כן.
באיזה קטע אבל מדברים על מערכות דינמיות? קטע שנגיד יש מערכות, אז מדברים על האינפיניטי שלהם או על שתיים שלהם?
מדברים על ה... לא, אני לא. אני רוצה... אוקיי, תראה, אני רוצה לדבר על... מערכות דינמיות לא קומוטטיביות. לא, יש לי איזו מטרה אחת. גם אותה אני לא בטוח כמה אני אספיק זמן. השאלה כמה אני מסכים להשאיר בלק בוקסס, ואני לא רוצה להשאיר בלק בוקסס. אז אם אני רוצה להסיק את המטרה הזאת, אני צריך יותר על דברים אחרים.
ולכן נספיק היום אם תתחיל לדבר על נוקליאריות.
אז אני לא יודע אפילו, אני פתאום הגעתי למסקנה שאולי אני אשאיר את הסיפור של נוקליאריות וזה לשבוע האחרון בכלל. הייתה התחלת לעשות את זה אחרת, אבל אני אומר שאני לא... יש כמה דברים שלא רציתי לוותר עליהם. לא יודע, אולי נעשה מקסימום איזה שיעור השלמה אחד בחופש.
אפשר שאנשים ירצו.
שאנשים ירצו.
לא, רגע, נושאים תרגילים כבר.
לא, אמרתי 50%.
וואו.
רק depending on the numbers.
וואו. אני אשמח לעשות הרצאה.
רגע, לא ראיתי שמחר אתה לא מרצה בסוף.
כן, שוב הודיעו לי כזה רגע לפני
היית אמור להרצות בסמינר?
הייתי אמור להרצות כשווידיק הרצה והייתי אמור להרצות מחר.
על מה היית אמור להרצות?
על להוכיח את פלוקס אפרוקסימיישן. דווקא זה ממש נחמד.
שכחנו אלטו אינבריאנס.
זהו, אני הולך לעשות תזכורת מההתחלה. אני הולך לעשות את מה שעשית עם הטופולוגיה ואז זה ואז
ויש את דני וייס.
דני וייס מחר.
זה לא נורמלי לעשות את זה פרונטלית.
מה, את דני וייס? פה. גם כשהיה וידיק היה מפוצץ.
כן, אבל השבוע זה כבר, אנחנו מחרתיים באיזה סרט בקים ביום.
הבנתי.
זה לא אותו שבוע.
צריך לדבר אולי עם אורי, עכשיו התבטלו בטח כל הקורסים שהיו ב-150.
בדיוק, זה אחרת להעביר את זה לכיתה גדולה. אפשר לשבת יותר מרווח.
אולי שווה לשאול.
כי בהסתברות גדולה יהיה פה נדבקים.
כן.
זהו, אני הפסקתי להעמיד פרונטלית.
אני קיבלתי הודעה על הקורס שאני ממשיך למדפות.
כן, כי נראה לי יש פחות מסוג רישומים.
הבעיה ממדרשה שהרוב לא רשומים.
לא, מה שמשנה זה לא רק שהרוב לא רשומים, זה גם הגודל של הכיתה הפיזית.
כן.
זאת אומרת, זו כיתה שהיא פיזית, אם יהיו בה 10 רשומים עם אחד, 10 נוכחים עם אחד חולה, וידפיק כנראה בהסתברות גבוהה.
השאלה,
בעוד שבכיתה נורמלית.
אם אתה שואל את פיינברג, אז לא מעניין את הרוב, הם לא עוברים פה עם היתר.
כן, אני מבין. זה הנקודה. אבל אני חושב שאם תיקח את הכמות של המדרשה ותשים אותנו בכיתה של בניין השני, כאילו הגדולה, זה יהיה בסדר, זה נכון. עושים חלונות, דלתות, בום.
בעיה מתמטית, כמה אנשים נכנסים פה עם שומרים.
circle.
אז זה בדיוק הנקודה, שכן, אנחנו ממש...
6 או 7.
טוב, בואו, אנחנו חכים למישהו?
לא,
לא.
נראה לי.
מיכאל עזב, בואו נגיד קודם.
כן.
שלהם לחזור, שתיות אחד.
עכשיו בינתיים לרחל על יונתן והנה.
הנה נראה לי שם, יונתן נראה לי גם. היי יונתן. זה היד שלי.
אולי אני אכתוב בינתיים רק משפט.
היינו חזר.
קיצר איתמר.
לא, זה איתמר חזר עכשיו.
היי איתמר.
שלום.
איתמר, אתה שורד את הכתב ואת הסאונד? איך זה נשמע, איך זה מרגיש?
הסאונד מעולה. אני פשוט
הכתיבה?
ספציפית באוטובוס ברכבת, ואז קשה לי לפעמים לראות את הלוח בטלפון, אבל זה הכל טוב.
Okay. Jonathan, Hannah, can you see the whiteboard? I mean, I know the camera is not that good, and maybe today I wrote a little bit small. How is it for you? Oh, you're not there? Okay, she's not.
If you can write a bit larger, it would be great.
I will try to write a bit larger, okay. Also, the pen is not the best one.
I brought you a blue pen, which should be good.
Okay, let's try it.
I'll check if I have other.
No, that's fine. Okay, so claim, I'm trying to write bigger, and I hope it will help you. Let S in B of H, but now it's in bloom. Is it okay? I mean, it looks okay here.
This is
Even better. So let S be in B of H, be an operator system, then yes, this is good. Then there exists a minimal S seminorm on B of H. Proof. So let phi lambda from B of H to B of H be S maps such that P of phi lambda is decreasing, chain of S seminodes since UCP from B of H to B of H is compact. It's BW compact in BW topology. And there is a subnet phi lambda, phi mu converging to phi. To some phi, right? And we only need to show that we need to show that p phi is smaller than all the p phi lambdas. Clearly, phi is an S map first, and since for any A rank C in H, we know that eta phi x of psi, which is equal to the limit of eta phi lambda psi c. Why is this true? Why is it equal to this limit? In the meantime, think about it. This is less than or equal to the limit of eta times phi mu x times psi, and thus phi c is less than or equal to pi to p phi lambda for every lambda. Again, since I mean, not just me, since it was started. So why is this true? Just this equality? I mean, what's the problem? The problem is that phi mu converges to phi in the BW topology. This is the weak operator topology. But I remind you that for bounded nets, converging in the BW topology is equivalent to converging the weak operator topology. This is something we mentioned and used before, and it's compact in the BW topology. So this is what we use, and this is less than or equal to that. So I know that the norm of phi of x, since this is true for any psi eta, so for some x in b of h, we have this, and this shows that p phi is less than or equal to p phi mu. But since p phi lambda is a subnet of p phi mu, and p phi lambda is a chain, then p phi is less than or equal to p phi lambda for any lambda. Okay? So by Zone's lemma, there is a minimal one. So by Zone's lemma, we are done. Fine?
Why you change it from lambda to mu? What is the?
Because phi lambda is not converging. I mean, I just know that I have a bunch of phi lambda, such that p phi lambda is a decreasing net. I don't know that phi lambda is decreasing or anything, or that it's converging. It has a convergent subnet.
This is the sub.
Phi mu. I know how to prove it for mu. At the end, I prove that p phi is less than p phi mu. But since this was a decreasing chain and this mu was subnet, so always there is another. I mean, any lambda will be less than some mu eventually. So it means that p phi is less than or equal to p phi lambda for any lambda. And then we finish with zones. Good. Is it okay, Alan? You're not satisfied.
No, it's okay.
Okay.
Maybe I should wear a mask so you can't see when I'm.
No, I do want to see your.
One is never satisfied.
So let S in B of H be operator system.
Compactness theorem doesn't work on.
Phi from B of H to B of H is an S map. Such that P phi is minimal seminorm, is minimal S seminorm, then phi is minimal. S projection, okay, it's not even clear that it is an S projection, right? S projection, minimal, and the point, phi of B of H is an injective envelope. Okay. We'll talk about uniqueness later. Proof. So first we need to show it is an S projection. before showing it's minimal, there are three things to prove here, right? 1, 2, and 3. Well, the fact that it is injective, we don't know it. So, 3. So let's start with 1. 1, the fact that it is an S projection. So we know that phi composed with phi is also an S map, right? Right? It's the identity on S.
So this theorem is due to Hamana?
Yes.
Okay.
So this is due to Hamana if you want to give credit, maybe. We're talking about 79. So since phi composing with phi is an S map, then of course it means that for any x in B of H, phi of x is less than or equal to phi of x, right? Because this is p phi composing with phi, and this is p phi, and p phi was minimal. No, let me write it like this in S map. So since this is an S map, and this is one thing, and we know that phi composing with phi of x is always less than or equal to f, phi of x. This is because this is phi of x. Phi is right. By minimality, very important. By minimality of p phi, we have a phi of x with equality. Yeah. Now I can do it not only for phi composing with phi, I can do this also for phi composing with phi composing with phi composing with phi n times, right? And same thing will still be true. So set psi to be 1 over n, like an ergodic sum of phi plus phi composed with itself 2 times plus phi composed with itself n times. Okay. So this means that I'm composing phi with itself. This is phi composed with phi. And let me call it this psi n. And psi n of x, again, by a similar computation, is less than or equal to phi of x. And by minimality, again, by minimality, psi n of x known is equal to phi of x. Thus, now I'm looking on phi x. I want to prove that phi is projection. So phi of x minus phi of x, right? Norm. Now I want to say that, right, exactly. So this is phi of x minus phi of x. And I can think of this as, well, this is equal to, by what we showed, psi n of x minus phi of x. And this is some kind of telescopic sum, right? This is well, you open this according to that, right? So it will be, and everything will cancel because it's a telescopic sample, you see it? So eventually this will be less than or equal to 2 over n. Right, I have 1 over n. This thing applied on x.
Times the norm 5.
The norm phi is 1, this. Right, and then we have this guy but applied on psi of x. So it will give her another power, and I subtract them. So I'm left only with the first element, which is phi, and the last element, which is phi composed with itself n plus 1 times. So it will be something like this. Maybe I'll write it. It will be phi of x minus phi composed with itself n plus 1 times, right? But the norm of this, I'm sorry, this is 1, not 2. This one is less than or equal to 2 over n. But the left-hand side is independent of n, so it's 0. So phi is that projection. Okay, now we're good to go to minimum, right? Minimality. What?
Funny trick.
Funny trick, right? Minimality of phi, but brilliant.
Yeah, it's like in this von Neumann ergodic theorem, the operator is the project. It's fun.
Yes. So now suppose psi is the next projection, and psi is less than or equal to phi. So this means that psi, right? This is not this inequality. This means that psi composed with phi is psi, which is phi composed with psi. I want to show that that phi is psi, since psi of x is equal to phi or to psi of phi of x. Right, by this, which is less than phi of x, then p psi is less than or equal to p phi, but p phi is minimal, so we have equality. We have equality. Equality by minimality of p phi. Therefore, phi x minus psi x is equal to, let me write this as, phi is an S projection, so I can write it as it is equal to phi is equal to phi composed with phi. And psi is equal to phi composed with psi. So I can write this as phi x minus psi x. But on the norm, I mean, it's just a game. We can now replace phi by psi because we have equality. So this is psi of phi of x. Do you see it? I mean, or am I going too fast? Before we proved that phi of everything is equal to psi of everything in the norm, right? Because we have equality. So I just use this. And now, what is psi of phi? Psi of phi is again psi. And psi of psi is psi. So this is 0. Okay.
Amana is Japanese.
Yes.
No, I see some.
It looks like a good sushi. I mean,
No, I see some analogy with Tomiya. Don't know. Yeah.
Okay. Yes. I think it's beautiful.
Yeah.
Now I have to show that what? So we're done, right? And I have to show. So you see that we're done, right? We show that phi is equal to psi. Now I need to show the third thing. So we know it's injective, and we want to show that that it's minimal injective, right? So minimality of phi of B of H. So okay, we already know phi of B of H is injective, of course. Assume we have somebody in between that is injective. So I have a projection psi from B of H to so there is right a UCP projection psi from B of H to 1 to I. So I is psi of B of H, but I want to think of it as go to B of H. So this psi is certainly so psi is an S projection. So psi is an S projection. It's a projection and reserves S because it reserves I, which contains it. So now I can also consider the composition of phi and psi. So phi composed with psi is certainly an S map. Is an S map, and of course its norm is less than or equal to the norm of phi of X. So by minimality we have equality again. By minimality we have that psi of phi of X is phi of X. And the way I want you to think about this, I want you to think that now we show that psi is in fact injective, is isometric on phi of B of H. So psi restricted to phi of B of H is isometric. Is isometry. But psi of phi of X minus psi of phi of X, this guy sits in phi of B of H. This guy sits in I, but I is in phi of B of H. So this whole thing is in phi of B of H. However, psi composed with psi is psi. So altogether I have 0. Do you see it? But it's isometric, so it's injective. So it means that phi of X minus psi of phi of X is 0. So this means that psi restricting to phi of B of H is just the identity of phi of B of H. So I, which is psi of phi of B of H, It's phi of V of H. And well done. Okay. Questions? So now we know we have, and we now know that any operator systems admit any injective envelope. Now we want to speak about uniqueness and other things. I wrote myself here something that if F is a minimal S projection, then I just wrote to myself. Note that I never said that if I start with a minimal S projection, then P of it will be minimal seminorm. This was never said. I'm just emphasizing this point. If we have a minimal seminorm that comes from a map, then this map is projection and it is minimal. But if I start with a minimal S projection, then its seminorm need not be. This is something later on we probably want to refer. And now lemma. If S in V of H is an operator system, and phi from V of H into itself is an S map such that P phi is minimal seminorm, is minimal a seminorm, namely such as in the proof, if phi from phi of V of H onto phi of V of H is the UCP such that the psi restricted to S is the identity restricted to S, then psi is the identity on phi of V of H. Okay, maybe I need to. I'm just saying that whenever, okay, this is an injective envelope, right? An injective envelope. I'm just saying whenever you have a map psi that goes from an injective envelope onto itself, no, I don't say onto. Whenever I have a UCP map from an injective envelope into itself, such that when it's restricted to S, I get the identity, then psi itself is the identity. So it's a sort of rigidity, right?
By the way, aren't all injective envelopes somehow isomorphic?
Yes, I didn't say it yet. I'm going to, I mean, I construct, but I need to say it. Do you see it immediate?
No. Does it depend on the embedding even? I mean,
yes. Yeah, okay, no, I don't know what is yes. I mean,
okay.
We'll discuss.
But it's not like super straightforward, like categorically we say your universal construction somehow.
No, the uniqueness?
Yes.
Okay, wait a second, and we'll discuss about it exactly. I just want to say to prove this rigidity lemma. So you know what? Let me leave it as an exercise. It is very similar, I mean, almost verbatim to the end of the proof of the similar, to the end of the last proof. No, it's not verbatim. It's written there. I mean, you just need to read it. Just read the last few lines that I wrote here with this psi, and it should work. Okay? More or less. I mean, you need to correct something because you don't know anymore that psi is a projection. But it's not a big issue. It's very easy. Good. So theorem let iota 1, kappa 1, and iota 2, kappa 2 be two injective envelopes of S. Then the map iota that goes from kappa 1 of S to kappa 2 of S, mapping, bless you, mapping kappa 1 of A to kappa 2 of A extends uniquely into a unital completely isometric map from I1 to I2. It means, in particular, it means few things. It means that the two injective envelopes are isomorphic in our category, right? They are isomorphic in a way that preserves the way S sits in them. So if both of them containing S, for example, then I have an isomorphism that is S preserving, and the one that we constructed contains S, right? Physically, concretely. It sits in P of H and it contains S. So any other guy will also, I mean, okay? And also, not only that there is a usage, there is a unique usage. So, so two things I want to say. I mean, it's important for me that you understand that we can think of it as if this usage is an S preserving, right? It preserves the way S sits inside it. Okay. So this is also the proof, but before, okay, maybe let me give the proof and then say a few things. So proof, let's take our injective envelope. I mean, what do I want to say? Okay, let phi B of H be the injective envelope we constructed. The injective envelope we constructed. Enough to show that kappa 1 from S to I1 has a unique extension to unital completely isometry gamma 1 from phi of B of H to I1. Why? Because then do the same trick to kappa 2 and I2, and then compose the maps. So consider, this map will be kappa 1 inverse, sorry, gamma 1 inverse composed with gamma 2. the one that goes from I1 to I2. So we have, right, we have that S sits inside phi of B of H, and kappa 1 into I1, and by injectivity of I1, there exists such a gamma 1. So there exists gamma 1 by injectivity of I1. Also, we have S that sits inside I1, and this is just the containment, identity map to phi of B of H. And by injectivity of this guy, there is a beta 1 here. So beta 1 composing with gamma 1 goes from phi of beta of H into phi of beta of H. And this is a UCP fixing S. Now use dilemma. By dilemma, and dilemma was somehow concrete. By dilemma, a beta 1 composing with gamma 1 with just the identity of phi of B of H. So gamma, this shows that gamma 1 is useless. Okay, but we're not done. But the range of gamma 1 but the range, the image of gamma 1 is right. Gamma 1 goes from something injective to something. So it's really need to be injective. Is injective sub operator system of I. So of I1, but I1 is minimal. By minimality of I1, gamma 1 is on. Hence, gamma 1 is uses isomorphism. If you are uses and onto, you are isomorphism in our experiment. Yes, here I wanted to say, okay, maybe it's clear, but just to be very clear, it's a uses isomorphism. I didn't write isomorphism because it's immediate from the fact that from I1 to I2 and conjugate. Just to be clear, okay? So, questions? Here, this part was very categorically somehow, nothing really interesting happening here. We have this map. So we have this map from here to here that is, this is an S map. And we show that S maps on this concrete one, and we use that concretely, the fact that it was concrete somehow. We use the seminorm, that it comes from a seminorm, and all the ideas. In the thing that I didn't prove, in the lemma that I wrote here, they told you that the proof is very similar to the end of the last proof. Anyway, it's very concrete, and then we know the uniqueness. So it has to be the identity, we have this rigidity. Once it is the identity, this means that gamma 1 is uses. All you need to do is to show it's onto. But it's onto something, it's onto a sub-operator system of I1. But this sub-operator system will be injected because whenever you are an image of right, this is what I want to say. I mean, okay, so once you know that this image is injective and it sits inside I1, then it needs to be equal to I1 by minimality of I1. I1 is the minimal injective envelope. So we're done. Okay. Now to your question. Suppose I give you two. So now we know that the injective envelope is unique. Maybe just a notation. And now that we know that the injective envelope is unique in certain sense. We can denote it by I of S. This is the injective envelope of S. We have one concrete injective envelope that contains S. So there is one. Right? We can think of IS as inside. If S is in B of H, then we can think of IS as containing S and contained in B of H, right? But this is just one realization. There are maybe other realization that doesn't fit inside B of H because this is something categorically. And also in B of H, there are more realizations. Also in B of H, I might have many more operator systems containing S that are the injective envelopes of S. But they will all be isomorphic in this way that there will be unit and completely isometric map isomorphism and in an S-preserving way. So in the way that they contain it. So that's good. Now you should ask me, but wait, Guy, recall that IS is a sister algebra. Is it also, are they also isomorphic as sister algebras?
Probably.
So something we never said, let's say it once and for all. Whenever I have an isomorphism in the category, an isomorphisms of sister algebras in the category of operator systems, then in fact, it's true in the category of sister algebras. This is very useful. I would say why. So I don't know, lemma, claim, general claim. In general, in the sense that maybe it's not the point to put it. Maybe I should have said it before, but I didn't use it. But now I'm just saying, whenever I clear sister algebras, if phi from A to B is a UCIS isomorphism between sister algebras, then phi is star isomorphism. So somehow, if you put two sister algebras in the wrong category and you tell them you are the same, then they're really the same in the right category also. This is okay. Before proving this, I just want to explain why is this very useful. One way to think about why is it useful. Imagine that. So next week I'm going to define what are G operator systems. Suppose that they have a group acting on operator system S by automorphisms of operator systems, right? By UCIS automorphisms. But suddenly, some of these S's will be sister algebras. This general claim tells us that the action will be an actions of sister algebras also. That each automorphism of this as an operator system, it will be an automorphism sister algebra. Okay, proof of the claim. I mean, we almost saw it, I think, even today. So what do I want to say? Let's say something like this. By the Schwarz inequality, by the Schwartz inequality, we know, right? We have so the fact that phi is UC means implies that phi inverse is UCP. Okay, so so phi inverse is UCP, and phi inverse of B. Well, I'm going to do Schwartz inequality on this guy. So this is, so on the one hand, I'm going to do a Schwartz inequality on what I have inside, and it is less than or equal to phi of phi inverse of B star B, which is B star B. Now, here I did the Schwartz inequality only on this part, and I applied phi since phi was positive. But now I'm going to apply Schwartz inequality on this part. Sorry, it goes, it's like this. What do I want to say now? Yes, this is bigger than phi of phi inverse B star phi of phi inverse B, again by Schwartz inequality. But this is B star B. So it's all equalities. In particular, the image of phi inverse is in the multiplicative domain of phi. Sorry. In particular, A, which is phi inverse of B, is in the multiplicative domain, of phi. So we discussed about the multiplicative domain, I think 2 weeks ago, 3 weeks ago. Thus, phi is multiplicative. Phi is star homo on A. And same goes for phi inverse, because it's all symmetric. So it's a star isomorphism. Cool, right? So this tells us also that this uniqueness is also a sister algebras. They're also isomorphic in an S preserving as sister algebra. Oh,
This is true for embeddings also.
right. You can. Yes. I mean, in some sense, yes. Yes. Need to be careful. I mean, in what sense? But
Just the UC sum to suboperators.
okay, let's do it. I mean,
Yes, okay.
you need both places to be. You need to be able to multiply in both of them. So.
Right. Okay. Sorry.
But that's fine. So you need to be able to multiply in your image, right? Like to.
Right. Okay. Sorry. You're
so.
right. Yes, you're right.
Up to something, you're right.
Sorry.
Maybe up to this. Yes, right. If I know that I'm uses, I mean that I have a uses containment and that the image is sister algebra.
Okay, yeah. I'm sorry.
No, that's fine. That's good. I mean, I'll be sorry. So we're done in this part. Good. Okay. So now I want to discuss about, I mean, stop everything. Let's take a break from operator systems for a second. I want to discuss about functions and so let me call it application. So suppose I give you a function system. Given a function system, So what is a function system? It is just a subspace, a space of continuous functions that is continuous functions onto the complex numbers that is closed under taking stars and containing the identity. And we could always embed it. We can always embed it inside some C of X, such that S separates the points of X. In fact, we can take X to be the states of S, right? State space of S, or the positive linear functionals, unitary positive linear functionals. And it's an easy exercise to show that S closure is isomorphic to the affine functions over the states of this convex space, right? So take maybe K to be this, and this is isomorphic to affine functions. So affine functions are functions that preserving the convexity.
Closure in
Convex
what
combinations.
sense?
So, okay, so I mean, embed first. First, it's not hard to embed this here. Okay, this is inside C of K with the usual supremum norm. So we can do this, and it would be a dense embedding in the dense embedding here, in the sense that the closure with this norm here would be so closure would be equality or dense, or the containment would be dense. I mean, exercises show this and show that this here is dense. In fact, this shows that any function system is affine functions over compact sets in some sense. Okay. Oh, convex compact set in some sense, which is this sense. Oh, you know what? Another way to think about it is the following way. In fact, any Banach space I can embed inside C of X in a way that will separate the points on the state space. So in fact, I don't even need the operator system, the function system structure. This is true for any Banach space even, for any subspace of a Banach space even. But this is very general, okay? What I'm just saying. And question: what is the most efficient X? Question: what is the most efficient? I don't know, I probably wrote it with mistakes, right? Let me write it again. Efficient. What's the most efficient X with this property? Of course, I need to define what I mean by efficient, right? And this is efficient. No, it's not efficient. Think about it. Affine function of K is very small inside C of K somehow, right? These are all continuous functions, and this is just the linear one plus the constants. Okay. So theorem of Shilov. I wonder if I should roughly rephrase it for you or exactly rephrase it for you. Let's do it roughly, and then if it will be enough, then I'll write it in the full version. So roughly, for every such S function system, there exists compact Hausdorff space called I forgot the name of this.
Boundary?
Yes, how do we call it boundary?
Shield boundary?
How does this character is called? I
Del?
forgot. Del, thanks. Del of S. Such that S sits inside
Del.
continuous functions of del of S. And the sister algebra generated, I mean, S separates points. I mean, the sister algebra generated by S is this guy with this containment. And for any other X, for any other compact Hausdorff X with this property, X contains, well, of course, what do you mean by contains? I mean, we can embed homomorphically this inside this, such that if I consider the restriction map to this map.
Restrict the restriction map?
What?
Like to restrict the restriction map to S? Never mind.
You take your function f
Can,
and you
sorry.
send it to f restricted to this.
Can, sorry.
Then this will be the identity in S. What do I want you to have in mind? I want you to have in mind the following thing. If S is the span of one Z and Z bar, and inside, let's say, C of the closed disk, continuous functions of the closed disk. Then we said before that we can think of S, the first time we discussed about a function system, that due to the maximum modulus principle, we can think of S as sitting inside C of the topos, C of the one-dimensional topos, right? How did I choose these topos? How did I know it exists? And isn't there somebody which is better? So no, the topos is exactly the Shilov boundary of S. And so we said this, and in fact, the last one. In fact, the V of S of this S is the top. I mean, that's an exercise. Well, it's almost clear. I mean, think about it. I mean, if I already remove a point from this T, somehow, I mean, things needs to be symmetric. And I mean, this should be minimal somehow. Okay. So this was the theorem of Shilov. And so is it okay that roughly speaking, when I said roughly speaking, I mean, what is the exact theorem I need to speak about? Containment in the sense of continuous homomorphic image, etc., right? And I just wrote containment, but you understand the point. And this Shilov theorem can be done also non-commutatively. This can be done non-commutatively. Definition. Now I'm going to do it formally. If IS kappa is the injective envelope, of S, then the sister algebra generated by S, by kappa of S, inside I of S is denoted by C star sub E of S and is called the sister envelope of S. Theorem, let S be an operator system and iota uses embedding U of H. Then there is a unique onto star homomorphism pi from C star of iota of S onto the sister envelope of S, mapping iota of A into kappa of A. What do I mean here? I mean that whenever you start with an operator system, there are many ways to embed it inside the sister algebra. But there is a unique way, which is the sister envelope, that has the following property. Whenever you embed S inside another sister algebra, A, such that A is sister of S under this embedding, so I know if this embedding is the iota, then this is sister of iota of S. I have my embedding, which in fact I can think about it as a proper inclusion because we already realized the injective envelope concretely as something that contains S, and this will be, and I will always have this star homomorphism to any such container. So in a sense, this is the smallest or the most efficient way to contain an operator system. So proof, I mean, this is immediate from properties of injective envelope of S. I will give you this as an exercise. And also another exercise is to show that the sister envelope of a function system is continuous functions over the Shilov boundary for any function system. So this generalize the Shilov boundary. Sometimes people call the sister envelope the non-commutative Shilov boundary of an operator system. Now, there are a few things I want to remark. One, there was also a notion of sister max.
Yeah.
You're familiar with this?
No, that's the natural question.
Yes, sure. So there is. And
This is kind of the opposite, right?
right, this is sister min. So this is the minimal sister envelope containing
So it has התכונה אוניברסלית.
כן.
לכל מישהו כמו בטא N בעצם.
זו תכונה אוניברסלית. This universal property says that whenever I represent S differently, then I have a map. This one, this is in a sense the minimal way to present S. This is one thing. And historically speaking, this question of the existence of the injective and the sister envelope was asked by Arveson in the 60s. And the first proof to this fact comes from Amana's work. So Amana proved it in his paper as the sister algebra generated inside the injective envelope. I mean, this is immediately. You should try and prove it. I mean, the fact that what do you need to prove? You don't need to prove the existence because it was hard to prove the existence. But what I told you that this is the definition, then you only need to show that these guys satisfy this property, and that's easy. I mean, this is a minute. Yeah, so this is one thing. Then Alveson saw Amana's paper, and he was very unpleased because Alveson had a program in his mind how the right proof should look like. And I didn't tell you about something that is called boundary representations, but let me tell you in a nutshell. If you've ever heard the notion of Choquet points or Choquet theory, so if you're familiar with it, then listen. If not, then you can stop listening. But there are this notion of Choquet point. These are points such that I can always. There is a unique extension of the restriction of the Dirac measure. So X is called a Choquet point. If there is a unique extension of the Dirac measure delta of X from S to sister algebra containing S. So in this, if X is such a point, we call it a Choquet point for S in A. And surprisingly or not surprisingly or classically, the Choquet points are not closed, and their closure is the Shilov boundary. This idea of Choquet points was extended non-commutatively to something called boundary representations. These are representations that when you restrict them to UCPs on your operator system, then you have the unique extension property. You may uniquely extend them into a UCP map. So this is the notion of boundary representation. What Arveson wanted is to construct the sister envelope as a sort of a closure of these boundary representations. And this was, I mean, this program was open for, I think, more than 40 years until Ken Davidson and Matt Kennedy solved it. A very nice paper.
You mean they proved it this way?
What?
You mean they proved it this way?
They proved the existence of a sister envelope, and so they reproved the existence of a sister envelope, and they realized it as the image of direct sum of enough boundary representations. Mm-hmm. In fact, it was equivalent to show that boundary representations completely there are enough boundary representation to completely embed the sister envelope. Yes, that's the point. Yes, and I think so. Okay, so yes. So next week we're going to speak about start speaking about dynamics. Just one more thing I wanted to mention is okay, never mind. Okay, let's leave it.
What?
Yes.
Are there cases where the C-star algebra generated inside the envelope equals the whole envelope? Like that the enveloping C-star algebra is the injective envelope?
I think that if you start with an injective envelope,
okay,
and then if you
start with an injective C-star algebra,
sure, and then if you remove few things from the injective envelope, then this should also work. Right? Even for natural things, I don't have in mind anything like that is small somehow enough so that.
But you say that
What happens if you take an injective, like already something injective, let's say B of H, and remove a few things to get something natural? What do I mean by that?
But maybe the question should be opposite. Like there is in general no reason that the algebra generated by S should equal I of S. I mean,
you're asking.
I'm asking in general what. Like I guess it shouldn't be true, but that the algebra generated by S inside I of S should equal I of S.
No,
S can also be a sister algebra itself. That is not injective.
Yes, sorry. You're right. You're right. You're right.
So I wanted to say in the commutative case, just take continuous functions over
Sure. Okay.
the interval. Something like this. Also, a good question to ask yourself: what happens in the commutative case? I mean, commutatively speaking, we have here a property, right? For any compact Hausdorff space X, we get a compact Hausdorff space Y, right? Because I of S will be a sister algebra. You don't. Do you see immediately it needs to be commutative?
What?
I of S.
In case
S is the commutative sister algebra.
Isn't that following form?
This is true. But maybe there's a.
In the example of the algebra, what the envelope is just restricting to a subset in this case.
I see.
So maybe that's the case in general. That
Again, say.
because in your example, right, the enveloping algebra is just restricting to the boundary.
No. I now I'm speaking. Suppose you start with the sister algebra. So there is no boundary here. So let's start with the sister algebra, commutative A.
Yeah.
Can you show that I of A, the injective envelope of A, is also commutative?
So let me assume A is separable. Okay.
Yes.
So, I mean, treat it as a compact metric space.
Yes.
Okay. I choose a faithful measure on a fully supported measure on it. Anyway, I just want to say I want to think of C of X inside L infinity of X.
You're right. Okay.
Wait. Okay.
No, I think you wanted to represent it as in B of
Yeah, it's inside L infinity. It's inside L infinity X mu, and L infinity X mu is injective. So, like
right.
it's
like we showed more or less today.
Yes.
The diagonal somehow of something that comes from B of H. You're right. This is what I need to say. And so I of A is injective, is commutative, and therefore any commutative, any compact Hausdorff space X admits a compact Hausdorff space Y that belongs to it that will be extremely disconnected, right? It will be injective, and it will be sort of a cover of it. So what is this?
So it's a cover. Yeah, because it's controlled.
So this is something that's called the Gleason cover of a space. If you want to read more about it, it is in some sense it is a Boolean. It has to do with Boolean algebras, and somehow because totally disconnected spaces are in one-to-one correspondence to Boolean algebras. This is Stone duality. Extremely disconnected spaces are in one-to-one correspondence to complete Boolean algebras. Complete means that you can take like infinite unions and things like that, and intersections. And once you have this in hand, then somehow you like if you want to associate to any. So somehow there are two ways to associate to any topological space a Boolean algebra. One is very minimal way. It's Kloppen sets. Sometimes it has nothing in it, right? Just trivial Boolean algebra. And there's a bigger one, like the maximal one. So this will be this guy. substance. Let's stop here. So, okay. See you all next week.
תודה.
Bye, bye, Hannah.
ביי, תודה.
Bye, Otan.
ביי.
Bye, bye.